This is a video on ordered hashing, particularly of strings, although it can be used for coding other forms of information as well. But it's basically there are two forms here. Either one is for numbers and the other is for strings. Now first we should look at a form of unordered hashing functions which maps a domain M to codomain or range S. Now the M is a binary string of length 2 power L dash, of length L dash, a number of size 2 power L dash, and the S is a number of size 2 power L, where L dash is greater than L. The entire information content that is there in this 2 power L dash must be hashed to S, which is 2 power L. Now I shall look at one form of hashing where L dash is equal to 2 times L. This is basically for reducing the length of the information to half. Now, basically the information length is reduced by half in the code. Now here the method is simple. Consider a number of L bits. The rightmost bit will be bit 0 and leftmost bit will be bit L dash minus 1, L dash bits, and so on. These will be the successive bits. Now the ratios associated with all of these bits is this: half, 1 by 4, 1 by 8, and so on, up to 1 by 2 power L dash minus 1. Actually, this is what is the ratio that is associated with it. What you will find here is so if we wish to reduce it by half, now we associate each of these bits, pair the bits together like this. Now we wish to code a number which is L dash bits in L bits, which is where L is half the length. So we pair the bits like this. Then we determine the ratio x such that the ratio associated here will be L by square of this ratio. So x plus x square equal to half is what we try to determine. This will give a value for x as, upon solving, as root 3 minus 1 by 1 by 2. Now for the next pair again, we will get the ratio. If we are to reduce x by half, we need, each time the ratios are decreasing by half. So we need x by 2 plus x by 2 the whole square equal to 1 by 4. This will give the equation x square plus 2x minus 1 equal to 0, which will give x is equal to, upon solving it, this will give the value of x is equal to root 2 minus 1. Now you will notice that the value of root 3 minus 1 by 2 here is less than root 2 minus 1. Very, very marginally, but it is still. You notice also that it is very, very close to half also. Similarly, if we take the third pair of bits, we will require x by 4 plus x by 4 the whole square equal to 1 by 8, which upon solving gives x is equal to root 6 minus 2. So you will get the following inequality. Like this, we can keep pairing all the bits and keep solving it. You will get root 3 minus 1 by 2 less than root 2 minus 1, which is less than root 6 minus 2. So the equation to be solved for will always only be the last pair. That is x by 2 whole power L minus 1. So L is exactly half of this. So x by 2, x by 2 power L minus 1 plus x by 2 power L minus 1 square is equal to 1 by 2 power L. So the value for x is what must be considered here. That value of x turns out to be, upon solving, x equal to 2 power L minus 2 times square root of 2 power L minus 2 plus 1 by 2 power L minus 2 minus 1. So this is the value that you have to take as a ratio for S. What you will notice here is that the reduction in the length is by half. So the weights that will have to be associated with the bit positions of S will be m into x, m into x by 2, m into x by 4, m into x plus x square, comma, m into x by 2 plus x square by 4 and so on. Whatever is the value of m is equal to 2 power L dash. So this will decrease. If these are the weights that are associated with the L bit positions of S, they will add up to m. But however, the weights, the value coded will be close to m, but within a string which is binary string, which bit number which is of whose length is half that of m. This same idea can now be generalized. Instead of pairing the bits like this, we can pair consecutive bits like this to code larger numbers and map a base which is greater than b greater than 2 to a binary base, b equal to 2 for coding a string of alphabets in a binary base. So that we can look at it now.